Hey everyone, welcome back to Real Analysis 1. This is going to be lecture 11. So, kind of following on with our previous section, exploring deeper into the topology of the real number line, particularly the structure of point sets, we're going to be discussing compact sets in this lecture. So let's go ahead and jump into it. I think for many this will be a section full of some pretty complicated mathematics, but I think it's super interesting, and I actually think if you spend the time, you will find many of these concepts to be pretty enlightening and pretty fascinating. So we'll call this section 3.2 compact sets. Okay, and so we'll just start with a couple of definitions. The first definition we need is what's called an open cover. So definition, let's let E be a subset of the real numbers. And then we say that a collection, and these are going to be a collection of open subsets, and we're going to denote it like this: O sub alpha, where alpha is in some index set A. A collection O sub alpha of open subsets of the real numbers is an open cover. It's an open cover of E, of the subset E, if E is a subset of the union of all of these open subsets, O alpha. Right? So if I take this collection of open subsets, O alpha, it could be infinite, could be finite. And if E is a subset of the union of all of these sets, then we call this collection an open cover. Another way to characterize an open cover would be to say the union, would be to say that the union of alpha in A of O alpha is an open cover if for all P and E, the subset E, there exists some alpha in A such that P is in O alpha, right? It's another way of saying the same thing, right? If E is a subset of this union, well, then for every P, this should be, for all P, for every P in this set E, well, I got to be able to go out and find some open subset in this collection of which P is a member. Okay. Another way to characterize it, which will come up in proofs that utilize it. So let's look at some examples. We got to generate some intuition regarding this idea of an open cover. So let's look at an example. Okay, so the first example is this. Let's let E be the open interval 0 to 1. Okay, and there's many open covers that you can imagine for this, but let's consider a particular one. Let's let O sub n equal the open interval 0 up to 1 minus 1 over n. All right, and we'll say this is for n equals 2, 3, 4, dot, 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 right? Infinitely many of them. We just omit the first one, obviously, because that would be E itself. Okay. Right, so what does this look like? Well, the union of all of these, n equals 2 up to infinity of O sub n, is going to be what? Well, the first one would be 0 to 1 minus a half. So it would be 0 to a half. And then union 0 to what? Well, it'd be 0 minus a third, so 0 to 2/3. And then 0 to 3/4, right? Right, so you can see the pattern here, and so on. Okay, and so obviously the upper bound on these open intervals is growing, right? So 1/2, 2/3, 3/4. The next one will be what, like 4/5, and so on. And so what's the limit of this? Right, so as n goes to infinity, this 0, 1 minus 1 over n, that's going to head towards what? 0, 1, right? right? And so that being the case, if indeed this union is a union of an infinite number of open subsets, then we can say therefore that ON from n equals 2 to infinity is an open cover of E. Right? And we can specifically say it because 0, 1 is in the union from n equals 2 to infinity of 0, 1 minus 1 over n. Okay, so it's basically, you start with some set, E in this case, and you come up with a structure for, in this case, a structure for all of the open subsets that are in your collection. And then you just show that, oh, indeed, like, if I take the union of all of these, then E is inside of it. E is a subset of it, right? And that's all we've done. This is kind of a simple example, although this one is nice because this one does, this is an example of an open cover that's infinite. Okay. Here's a general example that's super useful, which we'll see in some of the proofs to come. Let's let E be any, stress any subset of R. Well, it's non-empty. I'll put non-empty. So let E be any non-empty subset of R. Then we could say for every, well, for any, for every, we'll say every, epsilon greater than 0, the set of all epsilon neighborhoods of X such that X is in E, this collection, right, will form an open cover of E. Now, this is either obvious or you're overcomplicating it. Let's take a simple example. Let me flip pages here. Let's take a simple example of this example. Okay, so example, let's say that E is equal to just 3 elements, 1, 2, and 3. Okay, so on the number line, what do you got here? You got 1, 2, and 3. Well, for any arbitrary epsilon, so let epsilon greater than 0 be given, right? Any epsilon arbitrary. Then the epsilon neighborhood around 1, union, the epsilon neighborhood around 2, union, the epsilon neighborhood around 3 contains E. Right, that should be easy to see. What's the epsilon neighborhood around 1? Well, it's some interval surrounding 1. What's the epsilon neighborhood around 2? It's that one. Epsilon neighborhood around 3. It's that one. Right? So E is in this union. Okay. All right. So that's a nice, simple kind of example, but obviously one that can, this is true for any subset of R. So if someone's like, well, hey, I got this arbitrary subset of R, show me, give me an open cover of this thing. Well, this was one you could always use. Just choose any arbitrary epsilon and you could write this one out. Okay, so that's what we mean by an open cover. It's just a collection of open intervals, the union of which contains some specified set, right? If I want an open cover for E, I just have to find a collection of open sets that contain E when we take the union of them. So that's what we mean by an open cover. Let's talk next about what do we mean by a compact set, because the two are closely related. So we say that a subset K of R is compact if every, it's very important, every open cover of K has a finite subcover. Okay. So a subset K is compact if every open cover of K has a finite subcover. Okay. All right, so another way to kind of write that would be to say, well, just to elaborate, I guess, not fully rewrite it, but so if O sub n in alpha is an open cover of K, right, and K is compact, then there must exist alpha 1, alpha 2, alpha n, right, in this index set A, such that K is a subset of the union of I equals 1 to n of O alpha I. Okay, so all that a compact set is a set that where it's possible to take where for every open cover it's possible to find a finite subcover, which a subcover is just another word for a cover, but you know it's sort of a subset of an open cover. Okay, so basically K is compact if it is always possible to throw out all but a finite number of open sets for any open cover of K. Right? So this could, think of this as an infinite. If this is a finite set, then we don't have to worry about it. But if this is an infinite open cover and K is compact, then I need to be able to throw out all but a finite number of these things and still cover K. Right? Now it's very important to note that it isn't enough to show that there exists a finite subcover for K, right? Instead, we need to show that all open covers have a finite subcover, right? So if you wanted to show that K wasn't compact, one way to do it would be to come up with to devise an open cover of which you could show there is no finite subcover, right? But in order to show that a set is compact, we have to show that every open cover will necessarily have a finite subcover. Okay, so clearly a stronger condition than just finding a finite subcover. Okay. All right, so let's take a look at some examples of compact sets and some counterexamples, okay, and see what we see here. Again, examples are very important in math. If you haven't already, discovered that fact, all right? Obviously, I'm probably preaching to the choir with this, with anybody watching this one. If a set E is finite, it's automatically compact. So if a set E is finite, it is compact. Okay, let's see why. Let's take our set to be just some arbitrary finite set. So P1, P2, Pn, right? And let's say that O alpha, alpha and A is an open cover. Okay. This is a good one to start with because it shows you kind of the mechanism of how you show that something is compact, right? So let's say this is an arbitrary open cover, right? Then for each Pi in the set E, right, for each one of these guys, just pick one, arbitrary, there's going to exist some alpha I in A such that Pi is in that open set. All right, so P1 is going to fall into one of these, right? If this is an open cover, it has to be in one of these. It might be in lots of them, but it's at least in one, right? And so, okay, that's true for all of these values. So all n of these are going to fall into at least one of these guys. All right, and so how do we proceed from here? Right. Well, this kind of can be continued on. P1 is in E implies that P1 is in O alpha 1. P2 in E implies that there exists alpha 2 such that P2 is in O alpha 2. Right, and so on. So E is going to obviously be contained in the union of O alpha 1 or O alpha 2 or dot 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 or O alpha n. Now, if there's lots of examples for P1, you just pick one. Just pick one of them, right? But the point is that no matter what, it's always possible to whittle this infinite set down into a finite set and still cover E, right? No matter what these O alphas are. If this is an open cover, then I can always whittle it down to just n of them, a finite number, and I have a finite subcover. Okay, and so that means O alpha I equals 1 to n, is a finite subcover, right? And so that means that E must be compact. Okay, and so any finite set is compact. Okay, now let's take a look at a set that isn't compact. Okay, the open interval 0 to 1 is not compact. Okay, all right, so this is a bounded interval, but it's not a compact set, right? It's a bounded open interval. It's not a compact set. And to see that it's not compact, all we have to do is show that there exists an open cover that doesn't have a finite subcover. And so we can do that easily. Actually, we've already seen a good open cover to consider. So let O sub n equals 0, 1 minus 1 over n. All right, we saw this one in the previous example when we were trying to lay out what is an open cover. This is the one we saw. And we'll say for n equals 2, 3, etc. Right. So natural numbers minus 1. Right. We saw ours, so this definitely is an open cover, right? Because as n goes to infinity, this upper bound of this interval goes to 1, right? And so it does contain E. The infinite collection contains E. Okay, but it turns out that it's not possible to identify a finite subcover using this example of open intervals. Okay, and we can easily see this by we can generate a contradiction. Okay, we can generate a contradiction. Let's see. Let's assume there exists ON1, ON2, dot, 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 ONK. Okay, and these are going to be from this collection, ON n equals 2 to infinity, right? So let's assume that there is some finite collection such that the interval 0, 1 is contained in this union, ON1 or ON2 or dot, 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 or ONK. Okay. All right. So then, given the way that the intervals are structured, we'll say if we let n equal the max of these guys, n1, n2, nk, right? If we let n equal the max of these, then ON1 or ON2 or dot, 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 or ONK minus 1 or ON, capital N. What's that equal to? Well, it's equal to 0, 1 minus 1 over n1, or 0, 1 minus 1 over n2, or dot, 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 or 0, 1 minus 1 over n being the largest one, right? Now, because of the way these particular subsets are structured, everything that came before is inside of this one, isn't it? Right, so this whole thing is inside of this interval, 0, 1 minus 1 over n, capital N. Remember, capital N is the maximum of all of these. Okay. Right, but the problem here, hopefully it's obvious, 0, 1 is not in this thing. And why is that? Well, because 1 minus 1 over n is equal to n minus 1 over n, which is obviously less than 1, right? So certainly the points bunched up very close to 1 are going to be missing from this thing. No matter how big n is, it's always possible to find some values close to 1 larger than 1 minus 1 over n, no matter how huge n is. Right? And so the idea is that there's no way for this particular open cover to be whittled down into a finite collection of open sets. It still covers this set E. And so that being the case, E is not compact. So hence 0, 1 is not compact. Now you can kind of look at this and say, oh, actually, okay, so this is probably going to be true of all open intervals. Actually, you're always going to be able to construct some open cover that's like the one we just did, that kind of approaches this upper bound, this limit point that's outside of the set. And this is going to be a problem that you're going to see with basically all open intervals, isn't it? And you would be correct. And as we'll see later, this kind of example generalizes nicely. Here's another example. The set F, where we set F equal to 0, infinity, is not compact. Is not compact. Now in this case, you'd have an open interval, but this is also an unbounded interval, right? So the upper bound on this is infinite, right? And so we can show again that this one is unbound, is not compact, but kind of show it in a different way, although similar. Let's consider an open cover. We'll say u sub n is equal to -1, n, right, for n, a natural number. Right, and so what do you got here? You've got -1, 1, or -1, 2, or ... right? So you can see how this, an infinite number of these will certainly contain F. Right, so F is certainly in the infinite collection of these. Okay, but to say that I could find just an arbitrary collection of an arbitrary finite collection of these that houses this is obviously absurd, right? There does not exist n in n such that 0, infinity is contained in -1, n for obvious reasons, right? For obvious reasons, right? There's obviously going to be numbers larger than n of which this doesn't include, right? Right, and so this is an example where we have u sub n equals 1 to infinity is an open cover for which there is no finite subcover. Okay, so there's 3 good examples, right, where you've got, you've got a compact set, the first example, second example, and third example, both examples where the set is not compact. Right, and so you get the idea that this is a way to characterize. This is a quality that a set has. Right, a set is either compact or not compact, and it's an extremely useful tool later in analysis. But also you can characterize the real numbers as being a collection of what we'll see compact sets and not compact sets in a very specific way, which we'll get to in a second. Right, so what are we saying then? Well, the first theorem, right, which kind of, you can see it already, the kernel of it. You can see the kernel of this theorem in the examples we've looked at. The first theorem is the following. Every compact subset of real numbers is closed and bounded. Our first example, 0, 1, open interval, was not compact. It wasn't closed, was it? It was an open interval, right? So you had it was possible to come up with an open cover that included, that kind of had a limit process in there, right? And so that one failed. The second non-compact subset that we saw was 0 to infinity, obviously not bounded, right? And so this theorem says, hey, look, if you're a compact subset, you have to be closed and bounded, right? Every compact subset is closed and bounded. Let's prove this. This one's not too hard to prove. It's not totally obvious, but it is not too hard to prove. Let's assume. So we'll start by just showing that every compact subset of R is bounded, and then secondarily we'll show that it's closed. So the bounded part is very straightforward, I think. So let's assume K is a compact subset. Okay, we assume K is compact. And then consider just a basic open cover. A basic open cover that looks like this. Negative K up to K, open intervals, obviously, for K natural numbers. Okay, so consider this is kind of a basic open cover. And, well, this is actually this is an open cover of R. So consider a basic open cover, this thing, of the entire real numbers, right? Right. Obviously, as n goes to infinity, this will cover all of the real numbers. And so if it's an open cover of R, it's also an open cover of K. Okay, so this thing covers R, so obviously it covers K. Now, if K is compact, which we are assuming, K is compact, then there's going to exist K1, K2, ... Kn, right? Such that it's going to exist a finite number of these indices, such that K is contained in the union from I equals 1 to n of negative Ki, comma, Ki. Okay, so it's, this is all just definition, right? If K is compact, there exists a finite subcover. Here's an open cover here, so if it's compact, this subcover must exist. And so we can set n. So if we set n equal to the max, we'll set n equal to the max of K1, K2, ... Kn, right? Then, just based on the way this is structured, then K would be contained in negative n, comma, n. Right? And so obviously K is bounded above and below by n and negative n. So therefore K is bounded. Okay, so there's the kind of the proof that K is bounded. Just the fact that K is compact means, you can, for this particular open cover, which covers K for sure no matter what, you can identify some subset of open sets, in this thing, which, given the structure of this, means you can identify a lower bound and an upper bound. And that's the definition of bounded. Now, how can we show that K is closed? Okay. So how do we show that K is closed? Well, remember, to show that K is closed, we need to show that its complement is open. So to show that K is closed, we need to show that K complement is open. Okay, and so what that usually involves is finding an interior point of K complement, right? And having that interior point be arbitrary. So let's pursue that. So let's let P be in K complement. What we'd want to show is that it's an interior point. Okay, so P is just some arbitrary point in the complement of K. Okay, now for each Q in K, for each Q in K, we can choose epsilon Q, right? So the index set being kind of, the name of the point, right? There's potentially infinitely many points in K, so there's potentially infinitely many epsilons, right? So for each Q and K, let's choose epsilon Q greater than 0. And we'll choose it such that, what? Well, such that the epsilon Q neighborhood of Q and the epsilon Q neighborhood of P is empty. We can obviously do this, right? Because Q is in K and P is in K complement, right? So it's clearly possible to do this. Okay. Okay, this is always possible, right? And well, kind of to make it more explicit that it's always possible, we could say, well, so this is always possible, right? So you've got, you know, your P over here and you've got Q over here. It's always possible for me to choose 0 less than epsilon Q less than 1/2 the distance between the two. Right, that's going to put my epsilon Q neighborhood of Q there, and obviously it doesn't include the same epsilon neighborhood of P, right? They don't overlap. Okay, so that's possible. It's always possible to do this. Okay, so what does this get us? Right, so what do we have now? We've got that the epsilon Q neighborhood of Q and the epsilon Q neighborhood of P is empty. Okay. Well, what we can say then is, well, this follows, right? Because we took every Q and K. Because we do this for every Q and K, this collection of epsilon Q neighborhoods of Q such that Q is in K, right? Remember, Q is just all of the point. All of the Q's are just all the points in K. This thing here must be an open cover of K. Right? We saw an example like this, right? Where for any arbitrary epsilon, if you build, you know, a collection of neighborhoods around all the points in a set, then all of those neighborhoods together must be an open cover. Right? We saw an example of this. This was maybe our second example. Okay. Now, K is compact by assumption. K is compact by assumption. What does that mean? Well, it means this particular open cover has a finite subcover which covers K, right? And so by assumption, this implies that there exists Q1, Q2, ... Qn, such that K is a subset of the union I equals 1 up to n of the epsilon. Now the notation's getting a little crazy here, but just stick with me. Epsilon neighborhood of Q sub I of the point Q sub I. Okay, so K is a subset of finitely many of these epsilon neighborhoods. Okay, and so all we have to do is set epsilon, just identify the minimum epsilon. So just set epsilon equal to the minimum of epsilon Q sub I equals 1 to n. Right? Set epsilon equal to the minimum of this, and then what happens? What do we get? Well, here's kind of the magic, right? Then the epsilon neighborhood that we just chose epsilon, the epsilon neighborhood of P, and the epsilon neighborhood of Q sub I is empty. I'm going to set this less than the minimum. So we set it less than the minimum. And what that means then is that this intersection is empty. And this is true for all I. For all n of these. And so therefore, the epsilon neighborhood of P intersect K is empty, which implies that the epsilon neighborhood of P is a subset, not of K, but of K complement. This is what we need to show that P is an interior point. Right, and so we can say, and we see that P is an interior point of K complement. And so what does that mean? Well, P is arbitrarily chosen, so K complement is open, implies K is closed. Okay, so that's it's a little trickier, right? But I think the logic is relatively straightforward. Okay, so every compact subset of real numbers is necessarily closed and bounded. Okay. All right. Very good. Very good. Okay, that's interesting. Next theorem. Next up, the next kind of logical theorem to look at is the following. It says that every closed subset of a compact set is compact. Right? So if I have some compact set, I identify a closed subset of that compact set, it also is closed. Or sorry, it also is compact. Right? This doesn't say that every subset of a compact set is compact. Right? Indeed, I could easily give you an example of a compact set and an open subset of which that isn't compact. Right? So compactness isn't necessarily about the size of the set. It's something else. Okay, so every closed subset of a compact set is compact. Let's prove this one. This has some nice moves in it. Kind of much simpler than the previous, but still kind of interesting. Let's assume F is closed. Let's assume F is closed and K is a compact subset. And K is assume F is closed and K is a subset of, assume F is closed and K is compact. It's okay. Assume F is closed and K is compact. Assume also that F is a subset of K, right? So I've got the compact set K and F is a closed subset. There's probably way more expedient ways to state that. So assume F is closed and K is compact with F being a subset of K. Okay, so let's let O sub n being a natural number, be an open cover of F. So O sub n and be an open cover of F. So then what we can do is we can say that if I take all of these, O sub n equals 1 to infinity, and I union that with F complement, right? So this is an open cover of F. And then obviously if I join to that F complement, right? F is closed, so F complement's open. So this is a union of open subsets. And this thing here is going to be an open cover of the whole thing. This is an open cover of all of K. All right, so just to make this clear, so O sub 1 or O sub 2 or ... or O sub n or ... right? That is an open cover of F, right? So there's a lot of stuff in K that's not covered by this potentially. So all I got to do is just say, oh, well, let's also throw this one on then. So K is definitely in this open cover. It's in this union. Okay. Now, since K is compact, so K is assumed to be compact. So a finite number of these should cover K, right? So K is compact, which means that there exists, let's see, how do I want to notate? Well, I'll just write it like this. There exists a finite subcover of the above cover. So for example, and this is, so you got F complement. Oh, sorry. So you got, like, we'll say O1 or O2 or ... or ON. Some finite subset of this infinite collection is going to cover, well, that together with FC must cover all of K, right? K is in there. Okay. And so this also covers F, right? F is a subset of K. This also covers F, since F is a subset of K, right? So you got an arbitrary open cover, and now you can see because K is is compact, has a finite subcover, this very clever thing of just throwing the complement on there because it's an open set necessitates that F also has a finite subset, or a finite subcover. Okay, and so in order to do this, right, in order to be able to throw this on, this F complement, F has to be closed, right? F has to actually be closed in order to guarantee that its complement is open, right? That's why this only works for closed subsets, right? All right, very good, very good. Okay. Another interesting theorem. All right, so we're building up a picture of what a compact set is, and we're building up a picture of how intervals and open sets and closed sets all relate to compactness. And so this theorem is another push in that direction. So if S is an infinite subset of a compact set K, right? So if S is an infinite subset of a compact set K, then S has a limit point in K. Right? We've seen theorems kind of like this, right? Where you've got a set with certain qualities, and that is going to imply something about its limit points. And so here we're saying that S is, if S is, so K is some infinite set, and it's compact, then any infinite subset of a compact set has a limit point in K. Okay. And so we can prove this by contradiction. This is a nice proof. So a lot of the theorems in this section are they're very interesting proofs. They're like sometimes proofs are straightforward, they just kind of follow definitions. These are, I think, pretty creative and pretty interesting to see. And so like not only are you learning about compact sets, but you're also learning like some very kind of interesting proof techniques. So here's a proof by contradiction of this. So let's assume that no point of K is a limit point of S. Assume that no point of K is a limit point of S. Well, if that's true, then there's going to exist some Q in K, right? Some Q in this set K. Sorry. Yeah, I wrote that wrong. So assuming that no point of K is a limit point of S, then it's actually true for all Q and K. There's going to exist a neighborhood around Q. We'll just say an arbitrary neighborhood around Q. I'll leave off the epsilon, such that that neighborhood of Q contains at most one point of S. Okay, i.e. Q itself, right? That's what I mean to say. i.e. Q itself. Okay. Right, so what is it? Okay, so what have we said? So assume that no point of K is a limit point of S. So then for all Q and K, it's going to be possible. Remember what a limit point is? It's a point that's dense, right? There's points all around it, right? Meaning like no matter how close you get to Q, you can always find another point, right? So if no point of K is a limit point of S, then for all of the points in K, all the Q and K, I can come up with some epsilon neighborhood, some tiny neighborhood, such that that neighborhood contains just Q, contains only Q. And this is going to be true for all of the Q in S, right? Right? Remember, S is the subset here. This is going to be true for all of the Q's in S. Now, S is infinite, right? S is infinite by assumption. S is infinite. So no finite subcollection of what are we looking at here? N sub Q, N of Q. Right. So S is infinite, so no finite subcollection of this thing here can possibly cover K. Can possibly cover K, right? Right? And so that's the contradiction, right? Because K is compact, right? K is compact. I've just generated a contradiction, right? So therefore, no finite subcover of the open cover, and the open cover is specifically this thing, these neighborhoods around Q, Q and K. So no finite subcover of the open cover of this of K exists, right? And that's a contradiction because K is compact. And compactness means that every subcover has a finite subcover. And here's one that doesn't. Right? And so the problem here is this. Right? So when we remove that difficulty, none of this follows. Right? So it turns out that if S is an infinite subset of a compact set, then S has a limit point in K. Okay. Right. Okay, so compactness can tell you something about limit points of subsets. Okay. Now the next theorem is sort of an analog. Actually, I think I'm going to break this lecture into two videos. I'm going to end this one here, and then we'll pick up with the next theorem in part B of the video. Just because I want to make sure that I don't exceed an hour, and I'd say we have several big theorems to come. So we'll pick it up in part B. See you in a few.